In this video, we're going to look at how to do vector addition diagrams for forces on an object that are unbalanced. And in this situation, we've got a rocket pulling a box, or it's pulling a rope that's pulling a box across a sheet of smooth ice. Now I've already got the I've already got the interaction and free body diagrams down over to the left. So if you're not sure how to do those yet, go ahead and check out my other video on the topic. I'll link to it up here, maybe somewhere up there. Go ahead and check that out. So got this rocket pulling on a rope, pulling on a box, and it's speeding it up. So before we move on to the vector addition diagram, what we need to do is look at all of this stuff over here on the right. What's happening to the velocity? What about the direction of the velocity and the acceleration and all of that? So the velocity is changing, and that's given to us here in the problem. It says that it's speeding up, so our velocity is changing. If I look at the picture, we see that the rocket is moving to the right, so the direction of velocity is to the right. Now for the direction of the acceleration, if the object is speeding up, acceleration goes with the velocity. It's helping the velocity out. So in this case, it is speeding up, and so acceleration is going to point in the same direction as the velocity. And then because the velocity is changing, that means that the forces have to be unbalanced. And that is Newton's first law. If the velocity is changing, the forces are unbalanced. So now that we've got that out of the way, we can go to drawing the vector addition diagram. So I'm going to start off with drawing FG. Okay, draw that down. And the next one I'm going to do is the tension vector, FT. And then the normal force from the ice pointing straight up. And so what we have left then is a gap. There's a big gap here in the diagram, and that's okay. That's supposed to happen because the forces on the object are unbalanced. So my diagram should have some kind of gap in it. Now the next thing I need to add is a vector showing the net force. And the net force is the overall leftovers. It's the overall effect on the object, or the sum of all the forces. To figure out the direction of the net force, I look at the direction of the acceleration. And that's why that's important to get that out beforehand, so that we know how to draw the net force vector. So your net force, so F net has to point in the same direction as the acceleration, okay, which is to the right. And F net should also close up your diagram. Okay, so the way we draw F net should be pointing to the right, and it should close the diagram. So that's simply making a box here. Okay, and also draw F net as a dashed line to show that it's the result of all the forces, or the sum of all the forces. Okay, so let's do another one here, and it's a similar situation, except the ice is rough this time, so there's going to be some kinetic friction. Okay, so we still go through over here. The velocity is still changing because it says it's speeding it up. It's still pulling to the right. Okay, because the velocity is increasing, or because the object is speeding up, acceleration has to point in the same direction as the velocity. And so the forces are still unbalanced because the velocity is changing. Now we're going to do the vector addition diagram, and this is where it's going to get a little more tricky, because remember, when we finish drawing all four forces, we have to have a gap that allows us to fill it in with an arrow that points to the right. And so that's going to change how I draw one of my vectors. So it starts out pretty familiar. We'll start off with FG. I'll do my tension vector. Okay, I'm going to do my normal force. Okay, and this is where it's going to get different. Now, if the forces were balanced, I'd have to end my diagram right here, and so my friction vector would go all the way out there. But the forces here are not balanced. So there has to be a gap that I can fill in with an arrow pointing directly to the right. So the way I do that is I have to draw my friction vector a little shorter than the tension vector. And so that leaves this gap here that can be filled in with an arrow that points directly to the right. So I'll fill that in. And that is my net force. And so what we see here is that the gravitational and the normal force completely balance each other out, but the tension force is only partially balanced by the kinetic friction. Some of the, in fact, this much of the tension is balanced out by the kinetic friction, but the friction is not enough to completely balance it out. And so what we have left, the leftovers, is the net force.